So we start with what I call the TCP-IP architecture. Perhaps a bit contrary to what I said, which is a man-made accumulation of things, but it's a complex system, and the internet is a complex system. It's certainly perhaps the largest system that has been built. And complex systems, they can evolve by nature, but usually if they're man-made, there is some simple ideas behind them to make it work. What we will see here are those simple ideas. In fact, this module that we do now is the strict minimum that we need to be able to do the first labs. So we will go fairly superficially and quickly into a number of things, some of them in detail, some of them very superficially. And many of those we will come back to them more deeply in the rest of the course. So if you want, we do 2 passes on the compilation of this abstract material. First, we will see it very superficially to put a number of building blocks well in place and also some terminology. And then we will dive again into most of the things we will mention now. But that's the only way to go. In particular, to do the labs, you need to be exposed to a number of things very quickly. So this is more or less, this is following a subset, in fact, of the introduction chapter of the textbook I mentioned. The first concept that you hear when you hear about TCP/IP is that TCP/IP uses layers. So layers, what is it? Well, it's impossible to define without tautologies. So for me, it's just boxes that sit on top of each other. But it's a bit more than that. It is, what is special about communication is that you usually have more than one devices. What is not special is that most of it is done in software, and when you do software systems, what is the most important thing you have to keep in mind? No idea? Abstraction. That the hardware can support it, certainly. Complexity, and how do you tackle complexity? By making layers, or in software, they're called modules. You try to make your software modular. If you do a big system and you write a big program that is 30 pages to print, probably this program will be impossible to understand, fix, and maintain by anybody. So you typically write things that fit on the page, right? If it doesn't fit on the page, for me, it's too big. So you should split it into sub-modules such that you can understand in one page, and then so it's modularity. The layers are about modularity. Except now, because we have systems that communicate, you have modularity inside a system, but also in space from one system to another. So when a web server talks to a web client, you have the web part of them that are talking together. So this module that you want is called a layer. Layer typically means that we can rank them, we can order them linearly, which is often not the case. When you do complex, a true piece of system, you do a mind map or a UML diagram. Usually it's not linear, it's not nicely scaled from 1 to n, but it's a big network with lots of interactions. In TCP/IP networking, in networking in general, we try to avoid that so that there is no interaction from, for example, here I'm showing 5 layers, which is the state of things today in TCP/IP. Very often in books you find 7, but the reality is 5. The application layer does not have a direct interaction with the physical layer. It interacts only with the neighboring things below. That's what it means now. The application layer is the visible part of the internet. The application layer is, of course, the most important part. It's Facebook, it is the web, it is lots of things. That's the applications that use the internet. It's not the focus of this course, so we will not do programming for designing distributed applications, because there are many other such courses in programming itself, but also in distributed system. But we will still have one lab, Lab 3, where you will design your own small application. The focus there will be more on how we use the underlying mechanisms than what is the logic of the application itself. One word that is used is protocol in this context. A protocol may mean different things, and in general in computer science people are fairly relaxed about the meaning of things, so you need to know the environment in which something is used. A protocol in the context of computer networking means something very, very specific. It means a set of rules that govern the interaction of two things that are at the same layer. So when a web server sends information to my iPhone or my PC, the format, the rules, the actions that are expected concerning exactly that web application is called the protocol. So protocol is a set of rules, and the idea behind a protocol is that you can make it a standard. Standard in particular would mean that you can have a system on the left that communicates with a system on the right, even though they are not done by the same companies. Hopefully today, if you have a PC or a smartphone, you don't need to have the same operating system as the server that runs the software. So the protocol in the case of the web is a very, very simple thing. It just specifies a number of verbs like get, post, that say what you want to do. When your web client, your browser connects to a web server, normally the first thing it does is a get, which means give me the main file that is describing this page here. So that is what the application layer is about. The transport layer has the goal, is a programmer view. So TCP-IP has been invented by computer science people, so programmers essentially. So if you are a programmer, you would like to have abstractions that will make your life easier. Now there are many, many abstractions. Some of them have been fossilized, cast in stone into the concept of layers. And the transport layer is one of them. The transport layer is the simplest, the minimal way of accessing the network and accessing the network service from the viewpoint of a programmer who is developing an application. So if you write some application, the standard way is to use what is called the service of the transport layer. The service means the interface between the application layer and the transport layer itself. It means that if I have to send a block of data from one place to another, I will need to have to worry about whether this data is put in IP packets, what is the header, I mean, all that stuff. This is hidden from you by this transport layer. The transport layer of TCP-IP exists in two flavors. One is called TCP here, and TCP main job is to hide packet losses. When you send information through the internet, unfortunately, some of the packets may be lost. It's like if you send an envelope through the post, and if you don't send it as registered mail, it may be lost. That's the timeout. There's no signal in this room to indicate the hour. So I will finish this sentence, and we will do a 15-minute break in 1 minute. So packets can be lost. Now imagine you're transferring a video that is many, many blocks of information. If you want the video to be correctly received, you have to verify which packet is lost, which not, and the ones that are lost, you need to ask them again. You can do that, or you can use TCP that will do it for you. So TCP is providing the reliability service to the programmer. It does it in a very specific way by doing what we call a streaming service, which means that TCP assumes that you write the data into the network like you would do into a file when you write into a file, into a physical system, you expect that things are serialized. So TCP does the same. If you send 1 million of bytes, and if one byte in the middle or one packet that contains 1,000 bytes in the middle is lost, it will not deliver at the destination the remaining data until that missing piece of information is recovered. So that when you receive the data at the destination, you can always be sure that you're receiving the data as if things were perfect, in the sense you don't receive packet number 23 before packet number 1, for example. So the order in which the data was created at the source is exactly the order in which you will receive it at the destination. This is how TCP works. That's based on an assumption that is fairly made sense when you were transferring bytes. It makes perhaps less sense if you're transferring multimedia objects or elements of a page that could be reassembled in any order, but this is how TCP decided to do its job. If you don't want this, or if you don't need this, you can use UDP, which is the other transport layer option that does not at all do the same thing. It guarantees to you practically nothing other than the block of information that you are receiving is exactly the block of information that was transmitted. Or you receive nothing. In other words, a block of information is lost or is correctly transmitted to the destination as an entire block. So you will, for example, never receive half a block. So if you write some data, usually the application layer needs to put some metadata in it, explaining, for example, whether it is a JPEG file. If it's a JPEG file, you say that at the beginning of the file. Now, if you receive half a packet that doesn't have the MIME header, it is the MIME header of the application layer that says whether it's JPEG. You just receive a sequence of zeros and ones. You cannot even decode it. You don't know whether it's an MPEG file or a JPEG or whatever. So with UDP, we will avoid this problem by making the assumption that a block of data called a datagram is never fragmented. TCP does not do this assumption. TCP will deliver you the data exactly in the order they were sent, but like a long stream of things, but you're guaranteed that if you receive something, all the things before have come already. So you will also not have this header problem. Voila, we do a break and resume at 1:15. Let me first correct 2 bugs on these slides. The correct information is in Moodle. Here, the lab is from 11 to 3, not to 4, not to 2. Note that those times are just indicative. The hours that are given are the hours during which we are in the room to help you with the lab. But the lab takes more than 2 hours to complete, so you're expected to work more time than this. If you feel comfortable with part of it, you can also do it at a different point in time. There's an overflow slot on Tuesday. The weeks during which there will be a quiz are the weeks that are written there. 3, 5, 8, 10, 12, 14. So you have to be present there because the grade you receive there is part of your final grade. Right? At 11:15, for approximately 15 minutes, which is the time it takes to answer 10 questions on paper. I forgot to mention that you can exercise last year's quizzes. They are online in Google Forms format, so you can put yourself in the condition of a quiz and try them. We'll come back to that later. It might be a bit early now. Other questions? I said a few words about the transport layer. Of Of course, we will come back to it. We will have a module on it, and you will have a lab on coding your own small application layer that will be the best way to discover all the specificities of the transport layer. So that will be module 3 and lab 3. So as you notice, I'm going down from the top to the bottom. The network layer is really what is the internet. The network layer is the thing that provides full connectivity. Of course, when you would like to interconnect all machines, you could do a full mesh, but that's not what you do. If you want to interconnect all machines in an economical way, then you perhaps want to have intermediate machines that are called routers today, but that's fairly recent in the evolution of computer networking. The very first computers simply were networking computers together. If you had to send one file from one computer to another one, then you would send it to an intermediate computer that would eventually send it to another intermediate hop or to the final destination. That is called store and forward. So that's one of the easy concepts, but important concepts in computer networking. One way of interconnect many things is to interconnect in a graph fashion to a few neighbors and then forward the information from neighbor to neighbor. And you know, perhaps from other domains, that with a relatively small number of neighbors, by the properties of exponentials, you can very quickly reach a very large number of systems. So the very first computers, like BitNet, that was an ancestor of the internet, IBM SNA, used store and forward. Right. Questions? No. Of course, at that time, there were not so many computers in one campus. There was 1, 2, 3 computers. I'm talking here of the end of the 60s, beginning of the 70s. That went a long way. That way of networking went until the end of the 80s. But that's not the way TCP-IP does. The TCP-IP uses what is called packet switching. So the idea of packet switching is that you break the data, the file that you have to transmit, into an abstract entity called a packet that will become concrete when you transmit it, that is of a much smaller size, typically. This was used by the internet, but also by other networks like X25, Transpac, Minitel in France used that technology. And one aspect of it is, or an analogy, is to say that every packet is like a postcard, because now the entire file can be broken into several pieces. Typically, when you send a letter to someone, you put the address at the beginning. Now, of course, you will need to repeat the address in each of those pieces. And the machines in between are called the routers. So this is how the internet is organized today. You may notice that the routers are used to interconnect mail servers. So in fact, in the internet, we see two forms of transport of information. One which is store and forward at the application layer. One that is at the network layer that breaks information into small pieces and sends only packets. We will come back a bit later when we talk of the application layer about why we would not store and forward or not. Right now, if you've observed this little animation, you should have seen something special. Yes? Yes, all packets didn't take the same path. So that is intentional. It doesn't happen very frequently, but it may happen. The idea here that goes behind is that every packet should be an independent entity, like a postcard. If you have a long message to send to someone, you can send it in 20 postcards. You label the postcards 1 to 10, and the receiver will receive the 10 postcards, perhaps the same day, perhaps in several days. And if you put enough information in each of the postcards, it will be able to reconstruct the whole information. This is how the internet works today. Why do you think that we do that? proposing 4 possible answers. So here I'm not asking that we reinvent packet switching. It's been done once for good. But can you imagine one of the requirements? What was the motivation that led people to do this instead of the conceptually simpler thing that consists in sending the file to an intermediate computer that will send it to another intermediate computer, etc. I will close the poll in 5 seconds. So the majority of you think that's answer A, but a large minority thinks it's answer C. So answer C says it increases capacity. What does that mean? Who voted for that? Yes? So you can change the routes and it increases capacity. That's probably correct. By sending on multiple paths, you can have more capacity, at least for one end-to-end channel. If you have, like is the case of the internet today, a large number of flows, you can have some flows going there, some flows going this way, which you could do also with store and forward. So it's a good observation you made. But this is not the reason for it. In fact, if you send information theory, will say that's exactly the opposite. If you have a single path and you transmit hop by hop an entire file, you will have a better capacity than if you transmit packet by packet, essentially because multiple losses could occur on the path. For every loss, you will need to retransmit. And you minimize the total number of retransmission by doing it locally, repair the losses exactly where it occurred. So that's not the motivation. Very few of you said B, although it does reduce the bit error. No, it doesn't reduce the bit error rate, obviously. So if you said that, that's plain wrong. And the main reason is really the buffer size. So we discover here a property of the internet that is from the moment you have decided to send a lot of data to intermediate systems, the first issue that you observe when you try to do it, like you do it at the beginning by store and forward, the more people there are, the more your network becomes successful, then the more storage you will need in your intermediate system. Why do you need storage there? Yeah. Because there are losses. That's a good observation, but it's not the reason. Because routers don't repair losses. If you send a packet and it's lost, too bad. The router will not try to detect the loss and repair it, whatever. You cannot serve all at the same time. There is some queue, exactly. The job of a switching system is to receive things on inputs and forward them to the correct output. Now, you don't control exactly who is sending what, when, at which point in time. So it may happen that if you are a router, you have 10 input ports at 1 gigabit per second each. You have 10 output ports at 1 gigabit per second each. It may happen that at the same time, you have 10 packets from all 10 inputs that go to the same output. So during a time slot, you will be able to send only one of those 10. So the 9 others need to be stored locally. So a router is a queuing system. The simplest mental model is you have a queue at every output port. More sophisticated routers may have also intermediate queues inside because they may be built by little networks inside the box. But if we ignore this detail, we can think of a router as something that is very fast inside, but is by necessity limited by the speed of the outgoing links. So you have to store the data. Now imagine what would happen if you start storing video files. You have 10 video files that are being downloaded simultaneously. You will need to store 10 of them. Now 10 is a small number today. You can have millions of video files. If you need to store them, you will need huge amounts of storage, which you have in what is called content distribution networks. But the very first observation of the creators of the internet was, we don't want to do this. We don't want to store the entire data. We want to have routers that are as small as possible in terms of their storage. And even with today's technology, there's a good reason for that. The routers are real-time machines. They have to, real-time in the sense that they have to process the data very, very fast at the speed of the line. So whenever a packet comes, you have to analyze the destination address, decide which of the 10 or 100,000 or several thousand output ports, which destination you have to go. And as we will see through the rest of this course, you also do a few other things to the packet. You have to do that during the time it takes to transmit the packet, which is typically a fraction of microseconds. So you don't want to do complicated things, and in particular, you don't want to have to manage gigabytes of memory to find where the bytes are that you need to transmit next. So reducing the storage is really the main idea behind packet switching. Yes? Yes, I did not define capacity. You are right. It was perhaps, but it's not graded, so I don't want to argue on the details. Here by capacity, I meant the line capacity in the sense of information theory. Number of bits of information that you can transfer over a network. Is it increased by doing packet switching rather than store and forward? The answer is no. We'll come back to that in the transport layer. We will come back because that's a fundamental decision that had to be done and involves the transport layer. So we will study again. That's one important issue that remains in the internet today. Where should we do entire store and forward, where not? So we do it partly, but we need good reasons for that, and we will understand them a bit later. But the main job of the network layer, whether we use store and forward or packet switching, by the way, is to find a way to sort out all the things. In other words, we need an addressing scheme. To sort out all the things, the postal system uses the zip codes. So you read the zip code and you know immediately to which destination postal office you need to go. From there, you need still to find the person and the street number, etc., but it becomes a local problem. The zip codes in the internet are the IP addresses. So every point of attachment to the internet has an IP address. Those are sampled IP addresses from EPFL. For example, 128.178.71.22 is one IP address. This is a decimal representation, so it's when we say 128, it's really 100 plus 10 to the power 2 plus 2 plus 8. But in reality, those are textual representation of strings of bits. Because this was invented in the 70s. In the 70s, people were not comfortable with hexadecimal digits. So they used decimal representation instead of that. But we will need in our head sometimes to flip between the representation. For example, 128 means a number of 8 bits, which is 1 followed by 7 zeros, right? And similarly, 178, 71, 22. Which means that an IP address, or at least an IPv4 address, is how many bits? 32, right? It is exactly coded as 4 blocks of 8-bit each, and every block is represented by using the decimal representation of the address. It's trivial and obvious, but that is something we will need to live with all the time. Now, in fact, there are 2 networks today in the internet. They are called IPv4 and IPv6. So there are 2 packet switching systems. They are implemented on the same routers, but they're able to understand both types of address. It is as if the postal union in the world had decided to change all the zip codes, and they use only letters, for example, instead. So EPFL is 1015. Assume we change that, we say, no, now it will be A, B, C, F, J, K. So you would need to change all the addresses. And if you are a switching system somewhere, you receive a postcard, you'll have to know whether the zip code is of the one format or the other. The same has happened in the internet. There are 2 versions. The old numbering plan, but the current numbering plan is IPv4, the one I've shown a minute ago. And the new numbering plan is IPv6 and is 128 bits, so 4 times as many bits. And because it was invented in the 90s, where computer science education had become pervasive, and we're used to, electronic education, we're used to manipulate hexadecimal digits. So we write IPv6 addresses using hexadecimal digit, where 1 hexadecimal digit represents how many bits? 4 bits. 1 hexadecimal digit represents 4 bits, but it represents it exactly. It's a number between 0 and 15. There are exactly 16 possibilities that corresponds to 4 bits. So it's fixed format. Here is, for example, 2 addresses, 2001, which I would not read 2001, but I will do like everyone does. I will read as 2001, but it's not the number 2000. It's the hexadecimal number with a 2 zeros, and a 1, which is much more than 2000s, because, as you know, 16 is more than 10. We will come back to those addresses. We will need to understand them in more detail. Right now, we will just observe that those addresses have a main part and a suffix. Right? Before coming to that, the first thing to realize is that those 2 types of addressing are completely incompatible. If I send you an IPv4 packet and you speak only IPv6, you will not understand it. You are unable to forward it. So most machines, unless you have a computer that is extremely old, it probably supports both IPv4 and IPv6, which means it has 2 protocol stacks, one that contains IPv6, one for IPv6, one for IPv4. Same for routers. When a router receives a packet, it will know whether it's an IPv4 or an IPv6 packet. We will see how it knows which type it is. And based on that, it will analyze the address and perhaps do things a bit differently. We will abundantly discuss the implications of that. Apart from the addresses being different, there's conceptually no difference between IPv4 and IPv6. Even though you read a lot of marketing statements that say with IPv6 we will solve all the things that don't work well with IPv4, don't believe them. They're all selling vaporware. IPv6 is exactly the same as IPv4 in the concepts, not in the details, because it's been done later. A number of things have been fixed. A number of formats have been fixed. We will come back to that in detail. But there is, of course, a large difference with IPv6. There are more addresses. How many times more? Yes?
2 to the power 96.
Exactly. 2 to the power 96 more, which is a very, very, very large number. Right? So 2 to the power 32 is 4 billions. So IPv4 address, there are 4 billion addresses. When this was done, it was believed to be astronomically large, but now that everything has an IP address, and there are close to 8 billion people on Earth, 4 billion is too small. We will see with NAT, in fact, it's not too small, but it is believed it could one day be too small. And this is, of course, the same number to the power 4, which is an astronomical number. It is the order of the number of water molecules on Earth. So we can put an IPv6 address on each of them. In the internet, apart in this course, we usually don't see IP addresses. Instead, if I go to Google, I type Google, I don't type an IP address, right? So the internet uses names. Names are human readable in principle, depending on the language, because the names can be now using non-Latin alphabets. And, but as a first approximation, they are just equivalent in some sense to IP addresses. So every name, not strictly, we will see there are subtle differences, but as a first approximation, we can think of a name as another way of describing an interface. For example, ssc.epfl.ch represents the web server on which you can access the communication systems program. But in practice, it is the IPv4 or IPv6 address of this server. So there is not one-to-one, but there is a mapping between names and addresses. Now you're familiar with the naming concept. Unlike addresses, where the most significant thing are at the beginning, in names the most significant thing is at the end. So, for example, 2 letters at the end, like .ch or .nz, are country codes. They correspond to country. They are allocated to an authority inside a country that further allocates to whoever wants them. And then you have 4-letter or 3-letter that are more creative now and that correspond to different sectors of activity. You have info that we use for speak up, the .com, that's very famous, etc. We'll talk more about those in a second. But the first thing to realize is that the IP packets, so the packets that are used by the packet switching layer, are not forwarded, are not routed by names. So they don't contain the name. So this is where the analogy with the postcard doesn't work. If you send me a postcard on vacation, I encourage you to do so. You will write my name, my street address, and the zip code. But if you delete the zip code by doing in principle, you could find me also because all the addressing information is present in the postcard. In the internet, that's not the case. In the internet, there would be, strictly speaking, only the zip code, which wouldn't work in Switzerland because the zip code identifies only the post office, not your street number, not your house number. But imagine you would give a house number to every house that is in the domain of a given post office. We would put only this. In other words, names are not present in IP headers, so that means that we need to go to a service to find what is the IP address that corresponds to a given service. For example, assume you go to ssc.epfl.ch. I said this is a name that can be mapped directly to an IP address. When my web server, my web client, my internet browser, for example, when I click on a link that points to that server, the first thing that my computer will do is contact another server that is called the DNS server. DNS stands for Domain Name System, which is a server that contains all the mapping. If you want to send me a postcard, perhaps you go to local.ch to find my street address. So that's the same principle here. You would go to a DNS server and send a DNS query using an application layer protocol, which is the DNS name system. So the application layer, this application layer is an application layer that's used only for the internet itself. So my computer sends to a DNS server, in that case the one of EPFL, a question: who is ssc.epfl.ch? The DNS server, which is like a database, it's not exactly a database, but is similar to a database, will contain ssc.epfl.ch and also an IP address. And it will return it to my machine, and only then my machine will be able, using TCP in this case, of transferring a GET question to the web server that will then respond to me. How does the web server know my IP address? Included in the packet, exactly. So we could do the same thing, everybody has name, but of course there is a shortcut that is easier. When you send a packet to someone, you put also the return address. So every IP packet contains a destination address, but also a source address. So if you're a server and you receive a query, you don't need to do complicated things to know whom to respond to. You just get the source IP address and you respond to that IP address. So this is how the network layer, as a first approximation, operates. We'll come back to it a bit later for some more details. And this is the visible part that everybody knows more or less about the internet. Everybody, someday have heard of an IP address. People call them IP sometimes. What's your IP? Syntactically, it's incorrect. IP stands for the Internet Protocol, but okay. We will also call it an IP. Much less visible are the things below. You can have concepts like MAC addresses, and the problem here is that of the link layer. So the link layer is more mysterious and is justified by historical reason. We'll come back to it very soon. Right now, we still need to know a bit of it. So think of it as a cabling system. Cabling or wireless connection. So if you have at home a PC and a printer and you want to send the data to the printer, you need a way to connect the PC of the printer that perhaps is not as complicated as connected to the internet. This is the origin of things. At the origin of things, nobody thought of the internet when there were the first computer networks. The first computer networks were for business. They were not for finding, chatting over Facebook or whatever. So there were enterprise networks, essentially, and they were for connecting things like terminal to a main computer and to printers. So if you want to connect something to a printer, perhaps it's simpler than using the internet. You can use a USB cable and connect it directly. So the USB cable is an example of a link layer. It's a cabling technology. It's a bit more than cabling. In fact, the true cabling is physical layer. It has to do with the problem of multiple access. Multiple access. If you connect your PC to your printer and that's all, you don't have multiple access. But probably your USB thing does not have only the printer. Perhaps your keyboard is also connected via USB. So when the keyboard sends a signal, a packet to the processor, and the processor sends a packet to the printer, or the printer sends a packet to the processor, why would a printer send a packet to a processor? To indicate that it's printed, so it's usually acknowledgement. So there is a protocol. There's a printing protocol between a machine and a printer, and every protocol is practically always two-way, even if the main semantic is one. So even in that case, you still have to manage the fact that multiple systems are cabled together. That is the role of what is called the link layer. So the link layer exists today in a large variety of elements. The most visibles for this course are Wi-Fi, that's the one we use every day, and Ethernet. So we can think of the link layer as we put a box, an Ethernet switch, and we connect a number of things together, and they should work. And similarly for Wi-Fi, if we connect to a base station a number of devices, they should work together, even if two smartphones are trying to transmit at the same time, and if we don't use a physical layer multiple input encoding, then we have to manage the fact that there could be a collision. Now you can say to me, you could put a router there instead of a layer 2, of a link layer switch, and it's true, but the truth is you don't most of the time, and we will come back to the historical reasons and the implications very soon. Right now, we have to admit the fact that when we interconnect things, they're first interconnected in this way. And for this communication to work, for the same reason as we had at the IP layer, we need also addresses. When I send a packet from machine A to machine B, or to my smartphone, or to the router, which is also connected by Ethernet, for example, I need to know to which of destination it is going. So I need an address. Those addresses are called MAC addresses. They are typically 48-bit, which means this representation here, they're typically written in hexadecimal digit. They are very different from IP addresses in the sense that they have no meaning. They're just numbers. It's like your car. If you have a car, you have a plate with a number. The first two letters mean the canton that gave you the plate. The other numbers mean nothing, practically. They may mean something if you have a truck rather than a car. The first digit might be different, but the fact that your car is 510 or 508 doesn't mean that you live in Écublens rather than Vevey. It has no meaning with respect to the structuring of the network. The same is true for MAC addresses. MAC addresses are called hardware addresses. They are given when the equipment is manufactured, and they stay the same wherever you are. Whereas your IP address, when you're at EPFL, is an EPFL IP address, 128.178. something. If you move to somewhere else, if you go downtown, you will have a Swisscom address that will be a different address, not the same. But your MAC address will remain the same. Question? So the MAC address in principle is unique, although there is no police to verify the unicity, and some cheap manufacturers don't make them unique. The MAC address is unique because it is structured. The first 24 bits are allocated to manufacturers. So if tomorrow you do a startup that builds smartphones, you will receive a block of addresses. And this block, for example, 000C0 means Apple. Or no, I'm not sure. Yeah, I think this one means Apple. But you can look it up. It's called the OUI, Organization Unique Identifier. And in principle, it's the responsibility of the manufacturer to not duplicate the numbers. They are hardware addresses, and they are put as destination fields so that when a packet is sent from A to the router, B and C will also receive it, or at least the hardware will see it. And if the hardware is well behaving, that means if it's not working in packet sniffing mode, it will discard the packet that it's not for itself. In the lab, we'll use Wireshark and packet sniffing to observe things that come. And if B is NSA or the police or someone else trying to cheat on you, then you can see all the packets and you can receive them. The fact that the address is not for you does not mean that you can see it, of course. And so that's a potential security problem. At least as long as you need, as you use no encryption otherwise. Right? The destination MAC address is sent in the clear, but typically when you're at home, for example, on your Wi-Fi, all the things after, all the other fields are encrypted. So that a packet sniffer can capture all the data, but it will have encrypted data. And if the encryption is strong enough, then there's nothing you can do with the encrypted data. How do those two things interact? Well, there are many ways to interact, but the classical way is to, some terminology here. What in this context we call a local area network doesn't mean simply a network that happens to be in the same room. A local area network, in acronym LAN, L-A-N, means precisely a set of devices that are interconnected using MAC addresses. So here it means that the top computer and the bottom thing, which is a router, if I send a packet from the top to the bottom and if I happen to know the destination MAC address, what is the MAC address of the router will receive it. If the top computer on the left sends a packet to the printer on the right using the MAC address of the printer, nothing will happen because they are not on the same LAN. the left thing is not connected to the Ethernet switch on the right, so it will not work. So a LAN is a set of devices that can communicate using their MAC addresses as destination addresses, and it means that they are connected to the same switch or to the same collections of switches that collaborate, or that they are connected to the same Wi-Fi, for example. How do you interconnect them? Well, typically you interconnect LANs using IP routers. And this is why IP is called IP. IP stands for Inter-Networking Protocol. It's not NP, the networking protocol, it's the Inter-Networking Protocol, because at the origin of things, this is how things were. In a campus, you had one LAN. You had a small number of computers, one LAN, and the internet was about interconnecting campuses, and IP was invented for that. Of course, now the number of routers is much larger than the scale of those systems, and it's the dominant member. But this image is very important. That's the mental image of the internet today. The internet is thought of being a collection of local area networks, things that can communicate using MAC addresses, that are interconnected at a higher level using IP. And this is visible in the first detailed concept that we would need for Lab 0, which is the network mask. All machines that are in the same local area network can communicate directly using MAC addresses. But if I send an email to a mail server that is on the same LAN as me, I will still use TCP-IP to communicate. So there is a subtle thing to observe here. Two systems that are on the same LAN can communicate directly by using only packets that have MAC addresses. But to do anything useful, they always use IP. Right? So that's an important thing to observe. Of course, they don't have to. If you're a good programmer, you invest enough time, you can write a chat application that will work without IP and where you can chat with someone who is exactly on the same Wi-Fi base station, for example. You're not using any form of IP addresses, using only the MAC addresses. It might be a very good application to do if you want to be undercover. Nobody will ever see your application because all tools are based on IP technology. In other words, we're discovering one principle of computer networking today. Any communication between two machines must use TCP-IP, even if IP would not strictly be needed. Why do you think we have such a principle? It unifies, that's correct, but there's another more pressing argument. Well, you don't want to recode the thing whenever the assumption that you are on the same LAN no longer is true. So if I connect my PC to an application on another PC, a peer-to-peer application, or to a server, I don't want to have to use a given software that depends on whether the server is on the same LAN as me. What is the same LAN? That it means perhaps you're at TPFL and you are in the same building served by those Wi-Fi antennas that are here. But if I move to the next room, then the application would not work because I'm using another LAN attachment point. So for all practical purposes, you want a single piece of software that you do only once, because doing software is complicated enough. You don't want to have to do two different versions. But now if you do that, that becomes visible to IP, and this is why we have the concept of subnetwork and subnet mask. With IP, machines that are in the same LAN, no, I said something wrong. Machines that are in the same LAN communicate Whoops. Ah. Voilà. They communicate directly. So when the two machines that are in the red circle, when they have some data to exchange, the data doesn't go via the router. It goes directly from one to the other using the LAN technology, which in that case is probably an Ethernet switch. So they're connected to an Ethernet switch, and the packets will not flow through the router. So if we break the line that goes to the router, the communication will continue to be possible. That's the consequence of what we said before, or if you want, a design principles. Now, the IP addresses of all machines that are in the same LAN or subnetwork. So LAN is the word used, seen from the MAC layer, from the world of MAC addresses. It is exactly the same as a subnetwork, but the subnetwork is the word you will read when you open some text that has to do with IP. So if you're configuring something that has IP addresses, it's called a subnetwork. But subnetwork, for us, is exactly the same as a LAN, seen from the viewpoint of IP. Here, if you look at this map of EPFL, you see machines like the two ones that are in the red circle. Those one here. They are in the same LAN, but they're not in the same LAN as this one. Oops, I will steal 1 minute of your time. Now, for the thing to work, for internet to work, when a machine A sends some data to a machine B, it needs to know one important thing: is the destination in the same LAN as me? We need to know that because it's a corollary of what I said before. If B is on the same LAN as me, I will send it to B using MAC addresses. I will not go through a router. But if it is not in the same LAN as me, I need to find the address of a router and send it to a router. So you need a way to know whether you are on the same LAN as me. If I take the analogy of the post office in my futuristic view of the post office that would number all houses in a city, then an IP post number would have the postal code of the post office followed by your number. And two numbers that have the same prefix, the same post office number, would be in the same LAN. Here is the same, except there is not a fixed format. So at EPFL, we see that all machines that are in the same LAN, you can recognize that by looking at the first 3 bytes, which means the first 24 bits. So at EPFL, the first 24 bits indicate the prefix. Two machines that have the same first 24 bits are in the same LAN. At ETH is the first 26 bits. In other places, it's the first 16 bits. So most of the time it's 24, but not always. Therefore, we need also to signal to the machine what is the size of the prefix. And this is called the subnet mask, which is explained here. The subnet mask is a string of bits that are all equal to 1 in the positions that correspond to the prefix. It's a very old fashion of saying 24. You write 24 times 1 instead of writing 24, right? And you write that in dotted decimal notation, which gives 225, 225, 225, 0. So at EPFL, all machines have a prefix of 24 bits, and in the IP jargon that we inherit back from the 70s, we say that by saying the mask is 255, 255, 255, 0. Voila. That's all for today. Thank you very much for your patience for those 2 minutes, and see you tomorrow in the lab.